Our first speaker is Professor Tulika Mitra, who is an old compatriot of mine from Singapore, one of the leading people looking at spatial architecture, software-defined hardware as one of the projects that she was doing. And she's Provost Chair Professor at the National University of Singapore. She's going to talk to us about spatial accelerators at the edge. Please.
Thanks a lot, Shihai, for the introduction, and thanks to Wayne for the invitation, and thanks to all of you for turning up today morning after yesterday's great dinner. So appreciate that. So I'm going to talk about spatial accelerator at the edge. I think yesterday there was most of the discussion was focused on big systems, and I work on embedded systems. So I'm really looking at very small systems at the edge. And our goal is very simple. We would like to enable real-time data processing and response. So both the processing as well as the activation locally on device at the network's edge. And that could enable or unlock a large number of applications, as you can see. Of course, it has the advantage in terms of data privacy and security. There are some applications where you simply cannot deal with going to the cloud and back in terms of unpredictable latency. And sometimes you do not simply have the internet connection. So there are a lot of advantages of making the systems more intelligent, but at the same time, we face significant constraints in terms of the compute, the memory, and the battery life. And this is not getting better. This is in fact going worse. So Moore's law is allowing us to sort of still improve the compute performance by doubling every 2 years, whereas ERCOS is doubling every 3 months, right? So these systems are extremely sort of hungry in terms of both the compute and the power. But at the same time, I think the major constraints for any of these devices is really the battery life. So that today the GPUs consume about 700 watts. And that's really, really inefficient. And we do have some examples of systems that can do it more efficiently. Human brain, it's a biological system that can do this processing at about 20 watts of power. And if we are looking at something like my smartwatch here, we need to be at about 1 watt of power in order to kind of go through a day and do reasonable amount of processing. So the question that I want to answer is, or our group is looking at, is that how can I design the architecture and the compiler in tandem in order to actually get less than 1 watt of power? So of course, whenever we think of edge devices, I think most of the time we are thinking of microcontrollers. Yesterday there was a talk about how much you can push the microcontrollers. So the microcontrollers, of course, are extremely low power. So I was talking about 1 watt. So ARM Cortex M4. It's about 0.8 milliwatt only at 100 megahertz, but you can imagine that it has very limited amount of parallelism. So it's not good enough to kind of support the kind of parallelism that we need. Now, in order to support that kind of parallelism, typically in a processor, what you are doing is that you are trying to start with a sequential piece of code that's coming to the hardware, and the hardware is doing all the kind of really magic in terms of all kinds of innovations, the caches, the branch prediction, the superscalar architectures, and so on and so forth, out-of-order processing, which you see on the right for the AMD processor. But if you do that, you are actually spending a lot of power in just extracting the hardware, extracting the parallelism through hardware. So this kind of hardware-driven heavy lifting for parallelism is simply not feasible in the context of these kind of very, very small devices. So what do? So essentially, if you want to kind of scale the parallelism, you have to depend on the software to extract the parallelism rather than doing it through hardware. And that's where the spatial accelerators are coming in. And for me, essentially, all these accelerators have 3 basic principles. First is that we need to embrace the parallelism, right? Because if we want to have really high processing capabilities, then we have to have a bunch of processing elements. Now, these processing elements are far simpler compared to a microcontroller, right? So they're essentially an ALU and a little bit of additional logic. And we want to keep the hardware as simple as possible because I want to go for low power. So if you keep the hardware simple, that actually conserves the energy for you. So you can go for low power, but then somebody has to do the work, and this work is being done by the software. So you are actually exposing this whole thing to the software. And of course, you are asking the software to do all the heavy lifting right over here. Right. Now, this is just a kind of thought experiment. How much can I do with 1 watt of power, right? And I'm doing a lot of hand waving over here, but I'm kind of just looking at the numbers from Horvitz ISSCC to a 2014 talk. And if you look at that, and I kind of just take, so this was at 100 megahertz, I'm just looking at 100 megahertz, 0.9 volt, 45 nanometer, and if I look just at 8-bit max, right, 8-bit multiply accumulation units, if I had 1 watt of power, then if I just put max, how many max can I put over there? It turns out I can put roughly about 43,000 Mac units right there, right? And that gives us about 4.3 tops per watt, right? So if I didn't do anything, I just put these Macs over there. Of course, I cannot just put the Macs over there. I have to have storage. And again, if you just have 1 watt and you did not have any compute, you are just trying to put SRAMs over there, roughly you can put about 100 megabytes of SRAM on 1 watt power, and you can kind of make 100 accesses per cycle to the memory, right? And again, at a very, very approximate level. Now, notice that the storage actually needs to do 2 things. Either you store the data, because you don't want to go off chip as often as you need to. So you want to store the data on chip as much as possible, and you need to store the configuration because you need to be able to use the software in order to configure the hardware. So the way I see it, that the accelerated design choices are really trade-offs between these sort of how much on-chip compute, data storage, and configuration storage we can actually put in within 1 watt of power, let's say. That's what if my goal is that, then that's what exactly we are trying to do. Now, of course, there are a lot of spatial accelerators that are custom designed for a particular domain, in particular for Edge AI. There are a bunch of accelerators, bunch of startups that are coming up. And these are domain-specific accelerators. So essentially, most of them are targeting matrix multiplication. So what you are essentially seeing is that they have close to 0 configuration cost, right? So because you are not trying to do any software configuration, and they have very little storage cost. You have a little bit of a buffer here and there, but the data flow is mapped so nicely over here that you don't need to pay the cost. Now, what if I want to actually create more of a universal accelerator? If I want to bring that programmability, I want to support many, many different kinds of kernels over there, then I need to introduce the configuration storage, and the access cost. Now, remember, earlier I was saying that I can actually achieve, if I don't do anything else, I could kind of achieve about 4.3 tops per watt. And as you can see that these devices actually are achieving somewhat similar tops per watt, but of course they are actually at much mature nodes, not at 45 nanometer that I was looking at. But when I try to do this reconfigurability, then I need to kind of introduce a programmability into those devices. And that brings me to the CGRA spatial accelerators that we have been looking at for a while now, that actually introduces both the efficiency and the programmability. So interesting fact, when Owen asked me to give a talk, I actually thought I'm going to talk about CGRAs. Then I saw Jason is going to talk about CGRAs. So that pushed me to kind of, talk about CGRAs a little bit, but I'll compress it. And I'm going to talk a little bit about the new directions that we are looking at later in the talk. So, but just to go back to this CGRA spatial accelerators, what they are is essentially they're a bunch of processing elements, as you can see on the right. Right, it's a very, very simple design. So as I said, that you can actually have huge amount of parallelism, right? And instead of having the caches or the scratchpad memory where you go store the data, bring it back again and again, what you are having is these connections between the PEs. So you can see that there is neighbor-to-neighbor connection among the PEs. And essentially what your software needs to do is that the software needs to figure out how to map your code onto this fabric, right? So the software is responsible for figuring out everything and tell the hardware that this is what you need to do. And the hardware simply goes through that process, right? So one way of thinking about it is that each of these PEs have sort of a short configuration memory, and you try to map the loops of the program onto this device. And why loops? Because loops are where we are spending most of the time. So you try to map these loops. And the nice thing about loops is that you will actually go back, right? So you can have few configuration words, and you can map your application across this chip, and you are just going to kind of go through that that loop. So you can have a very simple hardware, and you can have low power, but you are actually pushing everything to the software. And CGRAs are essentially a data flow machine, right? And which has been there for a long time. I think the first paper was in this kind in 1975. So instead of bringing the instructions from the memory like we'll do in the microprocessor, what we do here is that we actually map the computation, as you can see, on the device itself, and you are just sort of flowing the data through that, right? So that's the whole idea of this data flow processor. Now, as I mentioned, that instead of letting the hardware trying to extract the parallelism, I'm now asking the software to extract that parallelism. So essentially, that means that I have these data flow graphs that I really need to map onto my hardware, and that has two parts. First part is placement, mapping the operations onto the different nodes, which is actually not so difficult. The more difficult part is this routing, right? How do you map this data dependencies through the links between the PEs, right? If you could go for shared memory, it was nice because you just write to shared memory, read from shared memory. But here, I'm actually trying to sort of map across the PE links, which makes the routing really challenging. So just to reiterate, CGRAs are spatial accelerators that you can think of as a same physical fabric, but depending on the application, you can actually kind of tune it to have different virtual accelerators, right, for each specific task. So essentially, you have a virtual or logical acceleration of the task. And so if you look at the Google TPUs, for example, this is kind of matrix multiplication only. And CGRAs can do that matrix multiplication, of course, if I map it properly, but it can do other things. So, for example, over here we have this is a real application that we have mapped onto our chip. So this is speech recognition, which has an FFT and then matrix multiplication and convolution. And as you can see that, I'm actually trying to use the same fabric, but as I'm going through the code, I'm actually reconfiguring it to do many different things, right? And that has actually two advantages. One is that, of course, you have the same small chip area, and you can actually use it for many of these different kernels. But the other advantage is that it has a really low carbon footprint, right? Why? Because today, most of the embedded systems has a system on chip that has over 50 IP blocks, right? And you are not using these IP blocks all the time. You are using them only when you are required to. So that is low dynamic power. But the point is that in order to manufacture this itself, you have this huge embodied footprint. I think Andrew was talking about that earlier yesterday. So you have this embodied footprint. And as you go, maybe this, I don't know whether it's easily, you can easily see it, but you can see that the embodied footprint essentially dominates when you are looking at consumer devices, for example, Apple Watch. But when you go to like data centers and things like that, the operation cost, that is the power you are consuming when you are executing, is far more compared to what you are doing in terms of the embodied footprint. So if I'm looking at sort of my embedded devices and small devices, what you need to do is that you need to really reduce that carbon footprint. And this is a paper that's going to come out in ICCAD 2024, where we are showing that you can actually get significant improvement in carbon footprint by replacing these SoC IP blocks with CGRAs and at the same performance level. Okay, So as I mentioned, that we started looking at the CGRAs for a while. Our first chip tape out was this high-cube chip, I think, which many people are using. And the reason we actually went for chip tape out, and I never did that before, is that it was very hard to figure out exactly what are the constraints we are facing in terms of the CGRA, because commercial CGRAs were not accessible to us in terms of the details, and that's why we went for this chip layout. One of the things that this high-cube CGRA does is that the connection between the P's, it takes one cycle to go from one P to another P. Over here, we have a single cycle multi-hop connection that allows us to go multiple hop in one cycle, which has the advantage that you actually kind of expand your neighborhood, which is a great thing, and as well as it enables the compiler to do an easier job in terms of mapping and a better mapping solution. I'm not going to go into the details, but following that, so this was in 2019, we did the chip tape out. Following that, we have a number of works where we are trying to sort of optimize this in terms of, how do you do the memory accesses? There is a lot of cost in terms of the CGRA when you are reconfiguring. You need to bring the configurations from the sort of the storage to the PPE, and that's actually a huge cost. How do you sort of manage that, as well as do a dynamic voltage and frequency scaling? That's the paper that we're going to present in micro this year. So with all these optimizations, this is the chip that we taped out in 2023. This is a CGRA along with the RISC code, and this is an 8x8 CGRA. We went for really ultra low power, so if you can actually you can run it at 200 megahertz, but if you run it at 10 megahertz, which is kind of sufficient for a lot of our workloads, you get only about 1.1 milliwatt power. This was at 40 nanometer process. We have about 582 GOPS per watt, but if we kind of did it at 22 nanometer, the estimate is about 1 TOPS per watt. And if we compare it against all the silicons that are available today, we have the highest GOPS per watt, even though we are actually running at only, we have manufacturing, we kept it out only at 40 nanometer processes. And then, of course, designing the silicon is one thing, but you really need to kind of bring it to life through the software. And I think we have been working at sort of data flow synthesis on the CGRA from 2012 onwards. I must say that, in 2012, we were trying to do this mapping on the CGRA, and then we thought, okay, we have a really nice theoretically optimal solution, and we kind of just left it there. But when we went for a real CGRA chip, then we realized that the complexity is much, much more. So you cannot really have this nice theoretically optimal solutions, but rather you have to sort of go for heuristic. And so you can see that we are trying to kind of scale that process through a number of approaches. And I think one of the things that works best in computer science, whenever we get into trouble, we kind of use abstraction. And this is kind of a hierarchical abstraction that we use that actually works pretty well. Basically, if you have sort of really very regular loops, then we kind of try to map it using all the techniques that are available from the systolic array side. So you kind of map the iteration space, and then following that, you try to sort of map the iteration space, and then individually you map each of the units. I'm happy to talk more about that if you guys are interested, but this reduces the compilation time significantly for really large CGRAs. And of course, I think there was a lot of talk about ML for design automation. And so it turns out that for this mapping, actually using graph neural networks enabled us to do certain optimizations, which was very, very difficult to do using our heuristic methods. And what surprised me really is that not only we achieved significant compile time reduction, but this is our technique, Lisa, which is kind of just using this graph neural network to figure out what optimizations to use. And it's sort of, we can map 70 out of 71 different combinations. But if you had used ILP or simulated annually, it can map only few of those combinations. So it really does enable a lot of nice things. And finally, I just wanted to show you that earlier I claimed that essentially what the CGRA is doing is that it is instantiating different data flow onto the same hardware fabric. And this is one example where on the left you have the Google TPU matrix multiplication data flow. So you can see that the flow coming from the left and coming from the top. And on the right, this is our automatically generated data flow for this matrix multiplication operation through our compiler toolchain. And you can see that it's roughly doing exactly the same data flow. And we have made this entire toolchain available. It's called Morpher, and if any of you are interested, it has the compiler, it has the simulator, it has the emulator. You can specify your own architecture. It doesn't need to be our architecture. It can be any architecture that you want to specify, and then you can map the algorithm onto this architecture, and you can try it out. You can even actually generate RTL code if you want. So this is a very complete toolchain. Of course, it's grad student effort, so there are bugs and there are problems. You have to deal with that, but I welcome you to try it out. And this allows us to sort of really map applications starting at very high levels. So, for example, you can have TensorFlow or PyTorch, whatever the application, and you can separate it out between the host processor, which in our case is the RISC, and the CGRA, which is on the right side, and we can kind of generate both the codes, and then we combine them together. And we have tried a number of applications, gesture recognition, voice recognition, and currently we are trying to do a brain-computer interface using this toolchain. And as I mentioned, that we also have an emulation platform. So that sort of, I kind of try to pitch about a more universal accelerator, but it turns out that there are certain domains, right, for which you can afford to have more sort of domain specificity in terms of, for example, the bit width, kind of compute unit you need, and so on and so forth. So this is one architecture where you can start one design space exploration tool that we have called Revamp, where you can kind of start with a very homogeneous system, and you can do this exploration to find out for your set of applications what would be the best sort of heterogeneous CGRA that would be good for you, and that can give you significant improvement in terms of area and power, but remaining at, of course, the same efficiency. So because you can actually design this kind of domain-specific thing. So we want to be a little bit more ambitious, and the next phase, what we are trying to hope to achieve is actually map some of the LLMs into this kind of a chip, right? Now, what is exciting to me is that this year we are seeing this emergence of native multimodal LLMs that can do audio, video, image, and of course text. Now, with text, right, it makes sense if you want to go to the cloud, but you can see that the kind of applications that is being enabled by these multimodal AIs, for example, math tutoring, where somebody is doing this geometry lesson on an iPad, or trying to find out where I forgot my glasses, right, using Google Gemini. These are like real examples of good match between an embedded system, because you really want to do it on device, and so that needs to be enabled in terms of the edge AI. Now, fortunately for us, while the models are getting bigger, this year we are also seeing that the models are becoming very, very efficient. So, for example, Microsoft released this 3.5 mini, which is actually a very, very small model, right? So about 6.6 billion parameters. And we are also looking at some of the 3 billion parameters models. So the models are getting smaller, but even then they are too big for our edge AI. And I'll not go into the details, but essentially, what are the opportunities that we have here? And it's no secret that you need a lot of matrix multiplication in order to do this attention mechanism, but at the same time, it requires huge amount of memory to store the model weights, also the KV cache. even for this small model, I need 3 GB in order to sort of operate on it, and that's not feasible on my edge devices. But fortunately, what's also happening, or maybe not so fortunately, is that you are seeing a lot of sparse attention mechanisms that are coming into play simply because the attention mechanism has quadratic complexity, and each of them have sort of a unique data flow, right? And sometimes you don't know the data flow until and unless you are actually executing. So how can I actually improve that situation? Now, it turns out that, of course, these things are very, very power hungry simply because I always need to go to the DRAM in order to get my model weights. My compute cost is very little, right? My compute cost, if I say that it's 1 watt, then my memory cost is about 200x that. So one possibility is that you can actually do sort of in-memory computing, which a lot of people are looking at. Here is our very small attempt to do the in-memory computing for a particular class of attention mechanisms, and that can lead us to very good efficiency. But that's not available today. So in terms of what's available to us today, what can we do? I think there was a lot of talk about quantization from Mitra, and I think that's a great way of reducing things and trying to make them sort of execute on this small age AI. So we show, for example, that 4-bit mini floats are pretty good for transformer models in terms of the inference. But what is also exciting is that so this is an architecture that has recently been proposed called MacMul-free LLM. And essentially what they're doing is that they are doing ternary computation, so -1, 0, and 1. So you can actually have 2 bits. Now, what's interesting is that my students actually tried to sort of implement this in a very, very parallel fashion on an FPGA. And for an U280 FPGA, if I use 2 FPGA cards, I can actually store the whole weights on chip in the URAM and VRAM without going to the HBM at all. And the moment you do that, you can get a significant improvement in terms of tokens per second and watts. So you can do about 5,000 tokens per second at 21 watt, as opposed to if you are just going to the HBM all the time, you are roughly at 100 tokens per second at 200 watts. So bringing things on chip can significantly improve the performance. Similarly, one can actually do sort of specialized attention layers. So here is one attempt to do it on an FPGA using sliding window attention. So this is meant for only sliding window attention, but what is really interesting is that by doing that, because FPGAs gives us this flexibility, so we can actually get 15x energy efficiency over the GPU, which I think is pretty interesting. But going from there to a specific accelerator for one kind of attention to more universal sparsity. And again, this is one of the works where we are kind of trying to do any kind of sparse matrix operations on an ASIC accelerator. So again, we can actually improve things a lot. But all these are sort of ASIC-based or FPGA-based, very specific design. So really the challenge, I think, is kind of really interesting going forward is that can we design a CGRA or maybe just a spatial accelerator that can support arbitrary sparse data flows onto your hardware. So, in terms of designing both the hardware and the software in tandem to enable highly parallel processing while handling the complex data flow dependencies. And of course, the low precision is in our favor. So that's all I have today. I'd like to thank all my students, my postdocs, and of course my collaborator in a lot of these works, Professor Yishwan Pei from the US. So thank you.
Okay, we have time for a question or two. Do we have some questions? Okay, so one of the issues you touched on, I think, in your revamp project is this non-heterogeneity of architecture. Do you think that balance can change now that we have these much more complex compilers, which have much more structural awareness? And how do you think the balance between what we put into hardware in terms of the flexibility of the singular architecture itself and the amount of work that the compilers have to do is changing?
Oh, right. That's a good question. So sorry, I mean, so the revamp project, maybe I did not make it clear. We are doing the design space exploration to find out the heterogeneous architecture, but we also have the toolchain for doing the compilation onto that heterogeneous. And the reason that becomes feasible is because our compiler toolchain Morpher actually has a template-based design. So the moment you do the design space exploration, you figure out this is the CGRA I want, heterogeneous CGRA, you can feed that onto our toolchain and it can automatically sort of generate the compiler for it. So yeah, so this is working for more regular code, I would say. If I'm looking at kind of sparse data flow, yeah, we are not there yet, right?
Your tools, can they be used to customize the granularity of the CGRA elements so that I might want different level of granularity? Sometimes might be bigger, sometimes might be smaller.
Yes. Yes. Yeah. Thank you. So we can so you can specify sort of in XML language, like how each of these elements PEs are looking like. So you can, for example, say that I just want an adder. I do not want full ALU. You can say I want 4x4. I can say 8x8. You can say what kind of network connection you want, how much storage you want. So it provides good flexibility.
Thank you to